All right, thanks very much. So yeah, I'm going to talk you through in this lightning talk in a few minutes, have a kind of a hello world to these two packages, which are very specific, namely Particle and Decay languages. So by the way, I have a bit more information that would fit in 10 minutes. So I put further reading in a few places, and I'll skip a few of those examples that maybe are a bit more advanced. So this one is a bit like an internet. So I'll just run it, but I'll start straight with the description of the particle package, which is the first one, mainly the core of this presentation. So particle data in short is particle data group, PDG, particle information, and MEC identification codes. And the main reason for this is some of these bits of information are often needed by all kinds of users in various occasions, and it's just nicer to provide something that does it quote unquote the best way possible, rather than having everybody trying to hack around for essentially the same piece of work. That's in short what I'm describing here in a bit more detail on the motivation for the particle data and in the MC identification codes. Again, because these are used by simulation packages, several ones. Sometimes they don't have the same IDs to describe or identify the same particle, and that's a bit annoying. So you want a way of exchanging and knowing what exactly is what in which Monte Carlo program. And of course, the central one is the PDG particle data group numbering scheme. That's what the package is about. It's essentially a pythonic interface to the particle data information, and MC stands for Monte Carlo, right? Simulation identification codes. That's what I'm putting a bit more in detail. So I'm going to browse you through some of the main classes and then show you how you can programmatically query all the information that is contained in the package. So this is still all text at the moment, but so you see that the PDG ID class, which is the main one, and then you see already two examples of giant tree or Pythia with its own numbering scheme, so its own IDs, and you have a few converters that you can play with if you want. So starting with the PDG ID class, let me just clearly import it from Particle, and you can just create a PDG ID for 2011 in this case, which is a positive pion. So no big deal. It just shows that it has created a class as in anything in C++ in Python. Now, if you wanted to go randomly creating anything, you actually see immediately in this case that is PDG ID is an invalid number. So you would not be surprised later on by that. And more usefully, you have a bunch of properties you can ask this PDG ID class, and the same functions or properties in this case can also be used as standalone functions. So if you want to query here whether this PDG ID, the pion corresponds to the meson, which is the case for the pion, that you can either do as a property of the ID instance or a standalone function. Nothing more. Now, if you wanted to know what all the properties that are available in this PDG ID, then you can query with info, and you have a very long list telling exactly what are typically yes and false for kind of has or is types of functions, but you also have some other ones such as the charge, the is valid, of course, spin, and so on. So I'll give you further reading on this if you want to, if you are interested at some point in translating between Monte Carlo programs, and you would want to use PTIDs or giant tree IDs, which are a little bit old by now, but still use sometimes. Then you can play with that. I'll let you do that. So I'll skip this thing. You can see you have various converters. Okay. So the other central class in the package is the particle class. So this is where we start to be able to programmatically do more things. So here I'm going to say I'm going to create a particle from its ID 2011, which you know is a Pi plus. So here it's just telling me exactly that, and you can have a nice display immediately with the Greek letters for the notebooks, right? Now, even more useful if you want to then go beyond that and you want to query all the information that are behind the scenes in our data files that have already massaged some information downloaded from the PDG, which is something that you will have to massage yourself by hand, and that can be quite painful, tricky, and we provide quite a lot of enhanced information for that net actually. Then you have these two main functions called find all and find iter, which is the first one gives all the search candidates that match some queries, some properties specified, or else you can iterate over those. So this is how you would go if you want to find all that that match JPSI. In this case, you only have a one item list, but that's where it is there. So it gives you a list of everything that has matched. Now, if you wanted to reiterate, and here I take the first item of the iteration, it only finds one particle because we actually specify the full name of one particle. I know that. I used to the standard phi, then it gets you immediately the particle. As if you were to check the type, you would see that it indeed is a particle. Now, at some point, you can start becoming a bit more fancy rather than just giving a name. So, for example, if you wanted to match and try to find all the pi type of particles of negative charge, you could just specify here the name pi, and then say charge I want -1, so you would get all the negatives, right? And if you're doing that, you would get all the charge conjugates. So nothing to worry about. And when you really want to start going fully fancy, then you can instead of providing these properties in the call, you could provide a function that allows you full flexibility. So I'm going to do that. I'm just taking DV units from this little PyHEP units package. I mentioned at the very top as an internet, so you can go and know more about that. But here you see it's broken, but essentially it's a one-liner where you say I want the PDG that has bottom flavor charges equal 0 and the mass is between 5.2 and 5.3 DGV. That's typically the B-meson, and that's why you get here. I have not specified any flavor rather than just say I want flavor bottom. So that's why you have both the particle and the antiparticle. You see 511 and -511 for the B0 and the B0 bar. And you have a nice printout by default that gives some basic properties. Yeah?
I have around 2 minutes left, Eduardo.
Okay, all right. So you can go quite fancy. The one I wanted to show, I didn't start 8 minutes ago. Yeah. Okay. Right. So you can go really fancy and see one liner again. If you want to say pseudo scalar charge reasons you could implement a trivial lambda function that would provide you everything. So you can go a bit fancy, trying to describe the particles. You see in notebooks you can get nice descriptions and so on. So I'll let you play with that. You also have literals if you want to pragmatically work with several particles. So that's again further reading, because as I said, I was provide far more than you could possibly see in 10 minutes. And again, if you want to know more about the data files, then you can look into this. Just showing one example here, using exploiting tabulate package. Then you could export all the information in the dictionary, also in a list, and then use tabulate to have a nice overview of a bunch of particles in a tabular format. So you can also do it in HTML, etc. Okay, RST if you want. We name it for any kind of information or documentation that you'd like to do. The other package is Decay Language. So this really is as very important in flavor physics to describe those so-called .decay files that are used in MC programs such as Vtfdk to describe the decay chains of any possible particle chain you might have. So you can programmatically do that. I'm going to give you an example here of a decay file where you see that there are two decay files, the two trivial decays specified with a bunch of aliases. If you don't know these things, of course, I'm not going to spend 10 minutes explaining what the files is, but you can more or less read that he's talking about the decay of one particle in two here, and so on. He also has some decay models. So if I take the main class, which is a decay file parcel, and I do that on the LHB master file, it's a big file. You see that it contains more than 500 decays there. It's 11,000 lines long. So you can parse it. It's not too long. It takes about 2 seconds typically. And then you can see that, yeah, it has parsed 506 decays in there. And you can have all the combinations, of course, that will give you thousands of combinations. So you can go around and read. You can parse all the information. You can also do it from a string. You can do multiple files at the same time. So you read like a combine if you want. And then more usefully, let me just parse these things. I need that information. You have all kinds of properties that you can acquire all the information inside the file. More usefully, you can also build the decay chain. So I want to know the decay chain for the DD+, for example. This is internally stored as a dict. And of course, it's even more important if you want to see what that looks like visually. It's much better than looking at the dicta. Becomes very quickly and comprehensible for the human eye, and you can do all kinds of things. So you can see that you can be very verbose if you want, again, on how that little file can be parsed and provide all the information. These are the branching fractions for Vtfdk modes. So you can do all kinds of things. You can specify, you can say, I want to switch off a branch because it's looking too complicated. So I put effectively a bunch of particles here stable. So you only see the first bit here, and so on. You can do charge conjugation, you can save it. I give you some handles on how to do that directly with GraphViz behind the scenes. This is further reading if you want to start looking fancy, because there are a few cross checks for no nonsense inside the parser again, so that I'll let you play with that. And the last point is, I finalize here. You can also build decay chains themselves programmatically. So you have a bunch of 3 classes, basically decay modes, decay .predicts and decay chain. So you see you are building by hand what you could find in a file, but you can do it programmatically. So you can do all of that, and you can get back all the information as before. And of course, visualize it as well as with the results of the decay file that you have done. And of course, if you flatten the whole chain, then it just gives you you see here all the decay chain, well, actually here. So you calculate the product of the branching fractions to give you the full visible branching fraction of all these decay modes. So a pi 0, pi plus, pi minus, and 2 gammas. And that's it. I'll stop here to avoid going more than an enlightening presentation. But I thought I would give you a hello world and a bit more information in case you want to play with this. Thank you.
Okay, thanks a lot, for this very quick overview of a package with lots of options. So definitely should look more into this. Unfortunately, I think also here we should move the discussions to Slack and continue with the next